Hello, I'm Sue Nelson, and thanks for joining me on Create the Future, a podcast brought to you by the Queen Elizabeth Prize for Engineering. Each year, there are an estimated several million earthquakes around our planet. Most of them go undetected, either because they're in remote areas or because they're so small. But there are around 17 major earthquakes annually that are magnitude 7 on the Richter scale and one that is magnitude 8. And to give you an idea of that scale, when an 8.9 magnitude earthquake hit Japan in 2011, it actually altered the distribution of the Earth's mass and caused the Earth to rotate slightly faster, shortening the day by 1.8 microseconds. And my guest, Zygmunt or Ziggy Lubkowski, is a seismic expert at Arup and a Royal Academy of Engineering visiting professor in geotechnical earthquake engineering at University College London. Ziggy, welcome to Create the Future.
Thank you.
Let's start with what a seismic expert like yourself actually does.
I look at many different projects, from building projects through to bridges, power stations and the like. And I'm looking at trying to prevent the effects of earthquakes on those projects, to minimise the impact, to ensure that key facilities remain operational, and so that the society is more resilient to these events.
Sounds like you're somebody who protects the destruction of the planet.
Well, I think that's probably going a little bit too far, but Mother Nature is not something that we can treat lightly. We've got to assume that these events occur. We have to understand where they can occur, how big they can be, and then we have a chance to actually design against them. And our knowledge and engineering skills are improving all the time to allow us to do that.
Have you ever actually experienced an earthquake?
Though I live in the UK, yes, I have, both here but also abroad, in Montenegro, for example, on a project out there, and also out in California, when I was part of a team investigating the after effects of the Northridge earthquake in 1994.
And how did it feel? What was it like?
Well, this was one of the aftershocks following that earthquake. I was in a tall building at the time, and it was very much as a swaying feeling like you may get on a boat when it's in a storm. And that lasted for 30 seconds or something like that, and then calmed down. So
for you, actually, that was... At least you got an experience of what it was like, but there's nothing on the scale in terms of like that one that, you know, actually altered the Earth.
No, I haven't been in a destructive event, and I haven't felt it from that perspective, but I've very much seen the after effects. And for example, I was out in Indonesia and Aceh following the Indian Ocean tsunami in 2004, and was working in trying to help the reparations following that earthquake and tsunami, which really devastated wide swathes of the region.
Indonesia, I've travelled around Indonesia. On the whole, apart from, say, maybe Java, a lot of the buildings are very low, and yet it still caused this huge devastation.
Yeah, I mean, in the case of Aceh, they had the earthquake, and it was a major earthquake, magnitude 9.3. So a lot of buildings suffered damage, some collapsed. The earthquake was some distance offshore, but then the big impact was the tsunami waves. And when you walk along the coast, along the north of Aceh province, there are areas where you can see the water levels were about 10 metres above land. So it just ripped the vegetation away. So any buildings within that region were just swept off their foundations. And you can see these villages and towns where they were just, the slate was wiped clean, literally. Some of the bigger buildings, some of the mosques survived because of the way they're constructed. They're on stilts, and the water blew out the walls, but then flew through the building, and they survived. But pretty much everything else was just wiped clean off the slate, and that meant a lot of people suffered as a result.
Is there a sort of scale in terms of, a bit like, let's say, the Beaufort scale? Is there a scale from an engineering point of view that you know that if an earthquake is going to be Richter 5, then you're likely to get some building damage. If it's 6, you definitely will. When do you, as an engineer, start to worry?
Unfortunately, it's not as simple as that, because it's not just the size of the earthquake, it's where it's located and also what the vulnerability of the building stock is. So in a country like the UK, buildings, because they're not designed specifically for earthquakes, if there was an earthquake, and we do get them, and if it would hit a town, we would see quite a bit of damage. If you get that same earthquake hitting, let's say, Los Angeles, you'd get very little damage because the buildings are built to resist those earthquakes, and therefore they're more resilient. Likewise, you could get a magnitude 8 in the middle of a desert without any buildings, so you might feel it, but nothing would be destroyed. So it's that balance between size of earthquake, the resilience of the infrastructure, and where it's located.
I'd read that traditional architecture in Japan, and also the Incas, that their buildings were built to withstand earthquakes. I don't know, I mean, you can tell me whether that's true or not, but I'd like to know whether what you consider from an engineering point is a good building to withstand an earthquake. Is it purely about foundations or flexibility or composition?
Okay, answering the first question, in terms of older buildings, in Japan, some of the pagodas were designed so each story, let's say on a 5 or 6 story pagoda, slid on the roof of the previous story, and it had a large tree trunk running through the top to limit the amount of sliding, and that created quite a flexible structure that in itself was more resilient. The Incas, and also you can think of the Egyptians with their pyramids, they built massive structures, the ziggurats in South America, and they were constructed in such a way that they would be resilient to earthquakes. What we see is what remained from that era. What you don't see are all the small buildings that people lived in.
Which probably got destroyed.
Yeah. And likewise, historically, people learnt about how, when something survived an earthquake, they built like the thing that survived, and that created a sort of a memory of what works. But that didn't stop things being built which didn't survive. The
practicalities of the pyramids, for instance, they're not a place to live anyway,
no.
For starters, yeah.
But in terms of...
Unless you count the afterlife.
In terms of current design, what we've been trying to do is ensure buildings are as flexible as possible. If you think about the difference between something like a large oak tree and bamboo shoots, or bamboo in a wind moves quite a lot. Wind goes, it's back standing upright. Large oak tree will sway in a large wind, but at a certain point it will crack and fall over. We want to ensure buildings are flexible so they sway in the earthquake, but when the earthquake stops, they come back to where they were. Now, we do that in a number of different ways. We can design concrete to be flexible, reinforced concrete to be flexible. We can use steel to do that. We can use timber. And it's all dependent on the detailing that we apply to the steel or the concrete elements that achieves that. Where we're moving to in the future, and people are doing it already, is using anti-seismic devices. So let's say putting buildings on bearings. So like your car has shock absorbers. Imagine driving your car without shock absorbers. It'd be very, very painful. So we put buildings on building-size shock absorbers to take the energy out of the earthquake and allow the building to survive. And there are very different techniques. So there are things called friction pendulum bearings that allow the building to sway. There are unbonded braces that allow certain elements of the building to be damaged in the earthquake and then replaced. There are many different systems that allow that more resilient building type to be created.
This is perfect for your background because you studied civil engineering to begin with before you did your master's in earthquake engineering. But even as a child, you were into building things.
Yeah, I loved helping both my father in terms of DIY, and there was a local tradesman who was doing stuff in the local community, and I was always there as the builder's mate, carrying bricks around and helping mix the concrete and so forth. And so I like getting my hands dirty, and I still do, much to my wife's annoyance when I don't get things done as soon as I promise I will.
That's perfectionism, isn't it?
Yeah, unfortunately.
Yeah. And were you any family members within the profession?
My father was an electrical engineer, and a number of my family parents' friends were civil engineers. So engineering was always part and parcel of what I grew up with. And my first cousin also went into civil engineering. Then he gave that up and went into finance to make more money.
Traitor. So what made you make that move then from civil engineering to earthquake engineering?
Well, I was always interested in the physical planet. So actually I did geography as one of my A-levels. Unlike the normal maths, physics, chemistry, I did maths, physics, geography. And so I was always interested in physical geography. And then I was very much taken by my soil mechanics lecturer at Kingston Polytechnic, Dr. Edward Bromhead, who was very much into slopes and such like. And I did my dissertation on his ring shear apparatus. So that really got me very much interested in that. And then I was very fortunate in my first job with Building Design Partnership. I worked on the Folkestone terminal of the Channel Tunnel and designed a number of the structures around that, and including the earthworks, which we had to design for earthquake loading. The Channel Tunnel itself was designed for earthquake loading because there were two UK major sort of magnitude 5 events in the English Channel in the 14th and 16th centuries, and as a consequence they needed to design the Channel Tunnel for earthquakes. And then I did some work on the earthworks at the Folkestone terminal, and that was really what got me into my first bit of earthquake engineering.
That's a good combination, isn't it? Because obviously when you see a geological map of the UK, it's quite interesting in terms of the differences in structure around the UK. Is there any particular type of soil where you just think, or rock and soil and structure are part of the UK where you think, no, that is not a good place? Is the Channel Tunnel, was that particularly resilient in any way, or did it just need help?
I think there are places in the world which are more at risk from earthquakes because of the geology. The UK, I wouldn't say, is one of those. For example, Mexico City, that's built for historical, socio-economic reasons on an old lake bed. It's about 40 metres deep, full of very, very soft materials. And what was observed in the large earthquake in 1985 was an amplification of the earthquake that was actually on the Pacific coast of Mexico, about 180 kilometres away from Mexico City. It was an amplification of motions between a natural period of about 1 and 2 seconds, equivalent to buildings with 10 to 20 stories. And that basically, just like the resonance on the Tacoma Narrows Bridge with the wind, there was a resonance in 10 to 20 story buildings in Mexico City as a result of that earthquake, and pretty much all of them collapsed. Small shacks stayed quite happy and weren't affected by that earthquake, but those 10 to 20 story buildings were really badly affected. And that changed the way we actually addressed the impact of soft soils on earthquake motions in the codes.
Now, we sort of briefly touched on the effects, the after effects of earthquakes that can be equally problematic in terms of like a tsunami. The most sort of well-known recent one was the one in Japan with Fukushima. Were you involved in that in terms of studying it?
I've read around the subject because it's always important to keep learning more about these events. And clearly, I also work on nuclear power stations, so Fukushima is a great case study as to what went right and what went wrong. So in the case of Fukushima, the earthquake occurred. The actual plant survived the earthquake very well. The emotions were greater than it had been designed for, yet it performed adequately. It shut down, and it was going through that shutdown process. Unfortunately, then the tsunami wave hit. The tsunami wave was much bigger than the local academics had predicted. It then inundated the plant. The plant still was performing well, but the water got into the diesel tanks, and diesel generators were being used as part of the shutdown process. And so that power was cut to the plant, and it was the water getting into the diesel tanks that was actually the cause of the problem. So it wasn't in a way, it wasn't an engineering problem. It was a problem with getting the assessment of how big the tsunami was or could be, getting that wrong.
You work with, as you say, nuclear companies, and the future for the UK is likely to involve new nuclear power stations. As an engineer, can you use things like flexible concrete on a nuclear power station? Because obviously you've got to worry about radiation and things like that. You know, how do you approach a nuclear power station?
There are very specific guidelines which are laid down in the Office for Nuclear Regulation in the UK, which set limits as to how much radioactive release you can have per annum as a result of external events. And those include earthquakes, aircraft impact, and so forth. As you quite rightly say, we don't want to have large radioactive releases. So actually you stay away from designing things flexibly. You design things to remain elastic. So you really want the building to, the concrete in the principal reactor vessel not to crack, not to release radioactivity, and that requires very good quality of design and construction to achieve that.
You do a lot of work in the UK, Middle East and Africa. Do the threats, the earthquake threats, obviously fault lines, we know that, but how are the threats for the Middle East slightly different to lower parts of Africa, for instance?
When we look at any site, we think about how big the earthquakes can be. And the first thing we look at is the tectonics and the geology. So if we're looking at Africa, for example, you actually have a situation where you've got the East African Rift Valley, which is actually trying to rip Africa apart. So the eastern part of Africa, Kenya, Tanzania, Mozambique, is actually moving towards the east, towards the Indian Ocean, whereas the western side of Africa is remaining where it is. And that split along the Rift Valley is a source of earthquakes. So we know if we've got a site in the near vicinity of that, the earthquake levels that we have to design for are greater. Likewise, in the Middle East, you have the Red Sea is spreading, which is sort of associated with the East African Rift Valley, and you also have a major fault running down through Israel and Jordan and into the Gulf of Aqaba, which is causing that to spread. So it's really, the key thing is having an understanding of where your site is relevant to these major tectonic structures. And once you understand that, you can try to assess the level of earthquakes that you have to design for.
As a job, though, this must be really interesting because you've got something slightly different each time and you've got to apply your knowledge and technical skill in a slightly different way. Is that right?
I think you've got to keep your eyes open. A lot of people, will pick up a code of practice for a particular country and just follow it like a cookbook. For my mind, that doesn't lead to good engineering. Good engineering is about understanding how the forces that Mother Nature provides affect your structure. I look at it from an earthquake perspective, but I also work with colleagues who look at it from terms of flooding or winds or other natural impacts. And you actually have to provide a holistic approach to how to ensure that those buildings or bridges or power stations remain resilient.
What would you say has been the most important lesson you've learned in your career so far?
That's a big question.
I know.
I would go back to what I observed in Indonesia following the Indian Ocean tsunami. You cannot design against Mother Nature. You have to understand the threats, and you then have to accommodate your design within those threats. And I think I get frustrated by sort of projects such as the Palm in the Middle East, where they now have a dredger that's constantly moving sand from one side of the Palm to the other because the longshore drift that causes the shape of the coast there is creating erosion on one side and secretion on the other side. So you need to put a dredger in to constantly move. That is not a sensible, sustainable piece of engineering. And, we often get caught up in, oh, that looks fantastic, rather than thinking about how it impacts on our environment. And I think we've got to balance clever and good engineering with the forces that are naturally there and, work together for a solution.
It's interesting that you did geography as an A-level. In a way, it sounds perfect for this type of engineering. Would you recommend that to people considering a career in engineering if they do love a subject that might not be your 3 or your 4 sciences and maths?
I mean, I did it by chance. I think the most important thing is people do what really interests them and then see where that takes them. So, if you are interested in earthquakes and you are interested in engineering, then geography does fit better than, say, chemistry.
There's also sort of geotechnical engineering with climate change as well.
Oh, very much so. That's where we're all looking at the moment and ensuring that we minimise the impacts of climate change in all that we do. But I think for me, as an engineer, you don't specialise too quickly. And actually, I'm not a great fan of the module system at university. I think everybody needs a good grounding in all the subjects, and only once they've got that grounding in all the subjects can you start to specialise. But that's my personal preference.
I know that there are certain projects that you're unable to speak about because of client confidentiality, but you are working on a power station at the moment that you can talk about.
Yeah, well, we've just finished work on the Wilva-Newid nuclear power station, and we've been assessing the size of earthquake that we have to design for, the potential for tsunami inundating the site, and also the potential for any of the faults that exist under the fault location of being what's known as capable. That means that they could move in an earthquake and cause a rupture at the surface. And so we've gone into a lot of very detailed analysis together with a lot of other companies and academics to assess all those issues to ensure that that site is very safe and appropriate to design a nuclear power station. Very much supported by our clients at Horizon. We've shared all our experiences on that project through presentations at the Institution of Civil Engineers, papers that we've written at conferences, and also other journal papers. So we've really been given a very much a green light to share our experiences and hopefully help other projects, similar projects in the UK and elsewhere.
That leads nicely on the fact that you became the Royal Academy of Engineering visiting professor in geotechnical earthquake engineering at UCL in 2018. Are you enjoying that, this sharing of knowledge?
Oh, very much so. And I think it's one of those things that you really need to do as a senior engineer, because we need to encourage the next generation to carry on doing the work that we're doing. And, I don't particularly want to encourage people to do earthquake engineering, though that's what I'm teaching, but I want to encourage people to do civil engineering as a totality, and whether they get into fluid dynamics or earthquake engineering or any other subject, I really don't mind, but we need more and more engineers, and I get the feeling that people are moving to those areas which are maybe where they'll earn more money rather than actually give back more to society. And I think, we as engineers have a great opportunity to give back lots to society.
Ziggy Lebowski, thank you very much for joining me on Create the Future. Do join me next month for another insight into the world of engineering in our Create the Future podcast.